Hi, welcome to Gear Revolutions. I'm Alex, and today I'm here with Dr. Hermann Stadtfeld of Gleason. And today we're going to be talking about transmission development for electric vehicles. So I just kind of wanted to start off by asking, what are kind of some of the primary differences between developing electrical transmissions and more traditional ones that people are used to?
Yeah, I think electrical transmissions, they have three things to watch for, even though the same three things you watch for in a regular transmission. But for example, NVH, the electric motor runs 20,000 RPM, maybe even higher. And NVH becomes, particularly for high frequencies, becomes a big problem. Then peak loads. An electric motor could easily, for several seconds, deliver a torque that's like 3 to 5 times higher than the nominal torque that the motor is rated for. And the gears have to survive that. And then also, besides the load carrying capacity and the peak load, the efficiency. Since it's an electric vehicle, so it's the efficiency that you have in a regular driving condition, but also when you take the foot off the accelerator, then the back driving should also be done with a high efficiency. Often people forget
Okay.
that. And in a combustion engine vehicle, that's not really any factor, but with electric vehicles, it becomes a factor because you would like to recuperate all the kinetic energy that the vehicle has back to electrical energy. So those things have to be considered in the calculations, the software that has to be available, but also in the manufacturing machines.
Okay, so if you're a manufacturer who's used to the more traditional combustion transmissions and you're shifting over and just starting to develop electrical transmissions, what are kind of some of the new, I guess, techniques, equipment, and software that you need in order to be able to do that?
Yeah, I guess that your question first addresses the traditional cylindrical applications because we also developed hybrid applications for electric vehicles. So let's start with the cylindrical applications. The software has to consider some of the factors that I mentioned. But first you have to look at the gear geometry, the manufacturing possibilities. So that is, we want to produce with higher spiral angles or higher helix angles. Then the hard finishing process has to be established. It is either finish hobbing, or it is grinding, or it's honing. Now, in order to get the NVH as well as the peak load, the flank form geometry, the topography, has to be modified. So we see not standard involute gears with just a lead and profile that's an involute, but we see length crowning, profile crowning, flank twisting, and even complex topological corrections. Now that has to be there in the software that considers it in order to predict how this gear is going to perform, but it also has to be available in the manufacturing machines because it means motions or geometry in the tool, etc. And we developed on those two levels,
Okay.
software and machines.
So speaking of things that Gleason has developed, what kind of stuff has Gleason made recently in this field, and can any of it help people with developing electric transmissions?
Now, referring to the show here, you will see at the Gleason booth, you will see a setup with an automatic loader, a threaded wheel grinder that can do topological corrections, as well as a double flank tester, a laser double flank tester, all in one unit, and also automatically loaded with a robot inside that transfers the pinions that are crowned between the double flank tester to the manufacturing machine, puts it in pallets, moves it out, and so on. So this automatic setup is actually really a textbook setup for manufacturing electric vehicle cylindrical gear transmissions.
Okay.
But if you want to know about the hypoid solution, we have this model, this working model here. We developed our first development step in hypoid EV transmissions is ratio between 1 to 8 to 1 to 15 in one stage. So you have one ring gear and one pinion. The motor is moved away from between the wheels so that the heat radiation goes evenly to both sides and not preferably, to one side of the one wheel and heats up that wheel to a higher temperature. And that one stage means you only have a pinion and a gear. You have two bearings on the pinion, two bearings on the gear side. You have a differential in there. So the simplicity of this transmission is really excellent.
Yeah.
And we see a lot of interest here with automotive manufacturers looking at the model and asking us how we do that. Also, we did some software development in order to assure this back driving capability. You can imagine the pinion looks almost like a worm, and if you try from a worm gear to drive a worm, that's always difficult. So we wrote a software that allows us to optimize the geometry to assure a high back driving efficiency for those transmissions. And we can show that here in our booth.
Okay. Speaking of software development, I know that one thing you guys have been developing a lot lately has been the GEMS software suite.
Correct.
And kind of one of the primary features of this suite is its ability to connect to a lot of different pieces of software in the industry. How important is that kind of cross-compatibility between different software?
No, I think that's very important because if you do a modern transmission design, I mentioned that at the ACMA day before yesterday, traditionally was that as soon as, for example, and you mentioned the GEM software, you develop a high-put gear set, the gear engineer that develops the high-put gear set, he would get as an input the ring gear diameter and basically the ratio, maybe the offset. And then this gear designer would design the bevel of the high-put gear set, optimize it, and then give it back to the transmission designer, the person that designs the transmission housing and the rest of the drivetrain. Now that is kind of a strange setup because now those people are confronted with, oh, that's the high-put gear set, and I'm really supposed to design the transmission, basically the whole vehicle around that. That's not really the way it's supposed to work. It's supposed to work the other way around. You get a system design with transmission and everything, housings, bearings, shafts, and also a concept gear already designed, and that goes then into the GEM software, and the GEM software would now design a highly optimized high-put gear set. Then that has to go back into system design software. Then additional softwares might have to be used, like for example, as soon as prototypes are manufactured, you need the metrology software that prepares the metrology, that evaluates the metrology, that establishes a closed loop. So really, if you can do that with an app-based system, that you have the GEM software, you have KISSOFT, for example, those would be the two major packages that always would work together in transmission design, then this forth and back, without any visible interface. You really jump forth and back, and the next software has already the data all available. You're not going in, you're not browsing in directories and retrieving some files and so on. So this is extremely important, and it makes the design work of a gear and transmission designer so much easier and more efficient.
Okay. So I know that Gleason has a lot of other software systems as well as just GEMS, and in particular, the software is designed to work with KISSYS. How do these two software systems kind of work together and support each other?
We wrote an interface. There's an XML interface between GEMS and KISSYS, and this interface would transfer, like what I mentioned before, now we would say, not make the high-put design first. Make the transmission design, get the whole concept with all the elements, and then tell us in GEMS where the bevel gear set is, what the major dimensions are, the size, the number of teeth maybe, or only the ratio, and other information. And then we design that high-put gear set. And that goes into that XML interface, and you could do it on the same computer, or you could do it in completely different locations. In the cloud, that's now possible. And you start it up, and you keep continuing the work that the other designer working in the KISSYS system was finishing. So the interface is the key, and we work on the interface. The interface started with only having base information, like the number of teeth, the pressure angle, the spiral angle, outer diameter module, and so on. And now we're moving on and also implementing flank form topography, so that we really have in KISSOFT the correct, complete high-put set. And then KISSOFT makes other analysis that are going beyond what is done in GEMS, like for example, efficiency analysis. They show speeds and they show temperatures, etc. So that's very good for the transmission documentation after design, but it's also good if this goes then in production and you have the first production result, like the temperature is a little bit high or there's an NVH problem. Now you go into that documentation and you know exactly where the dial is, where your problem is, that you can and how you can solve it.
Okay. Well, that's all we've got for today. So once again, I'm Alex. This is Gear Revolutions, and today we were talking with Dr. Hermann Stadtfeld. Thank you very much for your time.
Thanks for having me. Thank you.